There's a surprising development that suggests NASA could regain control of the long-lost Voyager 2 probe after picking up a faint heartbeat signal from it. Are you curious about the big secret NASA might be hiding regarding Voyager 2? In a twist no one expected, this legendary spacecraft has encountered something so extraordinary that it could force NASA into action. For years, we've hoped that Voyager 2 could reach interstellar space while still having enough power to send back valuable data. Voyager 1 managed to achieve this in 2012, and now Voyager 2 is beginning to follow suit in 2018. Even Joe Rogan is weighing in, questioning why NASA might consider shutting down such a vital mission. Could it be an alien signal, a cosmic hazard, or something even stranger? Get ready to uncover the bizarre truth about Voyager 2's final days before NASA decides whether to pull the plug on this iconic mission. Voyager 2's story began in an era when our curiosity about the distant cosmos led to daring explorations beyond the confines of our known solar system. Launched on August 20, 1977, Voyager 2 was an automated probe that predates its twin, Voyager 1, by just a few weeks. While Voyager 1 was designed for a faster trajectory, engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, set their sights on exploring the outer reaches of our solar system and uncovering the mysteries of giant planets that were largely unknown at the time. The launch of Voyager 2 was made possible by an unusual planetary alignment that occurs only once every 176 years. This rare alignment allowed the spacecraft to use gravity assists from each planet it passed to gain speed, shortening the journey to the outer solar system. The alignment was an opportunity too good to miss, and planners realized that missing it would mean waiting generations for the next chance. Although Voyager 2 was the first to launch, it was named Voyager 2 due to the specific route it would take, one that would allow it to pass by Uranus and Neptune later, though this meant a slightly longer flight. When Voyager 2 was first designed, the expectation was that it would only function for about 4 years, focusing primarily on exploring Jupiter and Saturn. The spacecraft was equipped with instruments designed to study magnetic fields, plasma waves, cosmic rays, and more. However, no one could have predicted that Voyager 2 would continue to captivate people around the world for more than 4 decades after its launch. Even the original flight team held cautious optimism, unsure of how far the mission would truly go. Gary Flandreau, an aerospace engineer, was the one who identified the planetary alignment that made the mission possible. In the 1960s, he conducted calculations showing that Jupiter, Saturn, Uranus, and Neptune would align in such a way that a single probe could visit all of them using gravity assists. This discovery saved NASA both time and money, as a direct journey would have required far more advanced technology and a much longer flight time. Despite the excitement, the mission faced skepticism. Could the spacecraft survive the journey through the asteroid belt and Jupiter's intense radiation belts? Early spacecraft had struggled with these challenges, but NASA pressed on, applying the lessons learned from the Pioneer probes. The goal was to gather new data about the giant planets and to push the boundaries of human knowledge. NASA didn't just prepare one spacecraft, but 2 nearly identical ones, each with distinct flight plans. Voyager 2's longer journey to Jupiter would allow scientists to observe the planet for an extended period, laying the groundwork for the spacecraft's even more ambitious goals. It was a risky plan, but the drive for discovery pushed the team forward. Little did anyone know, Voyager 2 would not only survive the journey but would continue functioning well beyond its expected lifespan, spending much of its time at the frontier of solar system exploration. Voyager 2's design was shaped by the technology available in the 1970s, and its remarkable endurance today only highlights how ahead of its time the spacecraft was. A standout feature was its memory, just 69 kilobytes in total, which is laughable by today's standards. Modern smartphones, for example, far outpace that in terms of memory. Yet, despite its humble beginnings, Voyager 2 was built for reliability. The spacecraft's systems were designed with redundancy, making it resistant to the kinds of failures that could have doomed it. The hardware was specifically designed to handle basic operations without relying too heavily on software, which was a brilliant move given the limited technology of the time. The spacecraft's memory and processing capacity may seem rudimentary by today's standards, but these systems were ingeniously engineered for resilience. The spacecraft had to withstand extreme conditions: vibrations from launch, radiation near Jupiter, and the freezing cold of deep space. One of the most fascinating parts of Voyager 2's design is its data recorder, which uses an 8-track tape system to temporarily store data before transmitting it back to Earth. This might sound outdated, but it worked reliably in the harsh environment of space. Despite the vast distances, Voyager 2 continues to send signals back to Earth. Each photon of data takes over 18 hours to reach Earth, and this delay grows as the spacecraft travels further. Communications with Voyager 2 are complex and time-sensitive, given the sensitive instruments aboard and the limited power supply. The spacecraft's power comes from radioisotope thermoelectric generators, RTGs, which rely on the decay of plutonium to generate electricity. As the plutonium decays, the power output gradually decreases, meaning that engineers must constantly make tough decisions about which systems to turn off to conserve power. Even with the decreasing power, Voyager 2 has survived far longer than anyone anticipated, and its survival is a testament to the ingenuity of the engineers who designed it. The spacecraft has built-in routines that allow it to correct any issues on its own if communication with Earth is disrupted. This ability to adapt and remain functional despite its age and the extreme environment of space has been key to its continued success. As Voyager 2 continued its journey, it entered the domain of Jupiter, one of the most exciting phases of its mission. Despite the challenges, including the planet's intense radiation belts, the spacecraft was able to capture a wealth of data and images of Jupiter. Its flyby, though not as close as Voyager 1's, provided scientists with valuable insights into the planet's magnetic field, plasma waves, and charged particles. The spacecraft's cameras captured iconic images of Jupiter's swirling cloud tops and the famous Great Red Spot, a massive storm system that has been raging for centuries. The data collected also provided scientists with a deeper understanding of Jupiter's magnetosphere. Voyager 2 helped show how Jupiter's massive magnetic field interacts with the solar wind, giving scientists a new perspective on the behavior of such a powerful magnetosphere. But the real excitement came from the moons of Jupiter. While Voyager 1 had already made headlines by spotting active volcanoes on Io, Voyager 2 helped confirm these findings, capturing detailed images of Io's volcanic eruptions. The spacecraft also gathered information on Europa's icy crust, hinting at the possibility of a subsurface ocean beneath its frozen surface. Other moons, like Ganymede and Callisto, were also studied, revealing their unique geological histories through their craters and grooves. Each moon turned out to be an intriguing world of its own, defying expectations and sparking new questions for scientists. One of the highlights of this phase was the different perspectives that both Voyager spacecraft provided, allowing scientists to track changes over time and observe phenomena like the volcanic activity on Io or shifts in Jupiter's weather patterns. The combined data from both probes proved to be invaluable, contributing to groundbreaking research. After completing its Jupiter flyby, Voyager 2 pressed onward, its trajectory adjusted by the gravity assist it received from the gas giant. The spacecraft was now on its way to Saturn, where another scientific milestone awaited. Voyager 2 arrived at Saturn in August 1981, about 9 months after Voyager 1 had completed its flyby. While Voyager 1 had already provided significant insights into Saturn's rings, Voyager 2's contribution was no less valuable. The spacecraft's instruments revealed intricate structures within Saturn's rings, such as braided rings and spokes, phenomena that had never been predicted before. These findings, coupled with measurements of Saturn's magnetic field and its interactions with the solar wind, deepened our understanding of the planet's complex magnetosphere. Saturn's moons also provided rich data, with Enceladus showing signs of recent surface modification, suggesting the possibility of ongoing internal geological activity. Mimas, with its massive Herschel crater, sparked discussions about the moon's violent past, while moons like Tethys, Dione, and Rhea offered new perspectives on icy worlds. One of the most iconic moments came with Titan, Saturn's largest moon. Voyager 2's contribution to the study of Titan was invaluable, providing additional imaging and data about its thick, hazy atmosphere. Though the haze prevented a direct view of Titan's surface, Voyager 2's instruments analyzed the chemical properties of its atmosphere, which led to theories about possible organic chemistry occurring there. This information set the stage for future missions, such as the Cassini-Huygens mission, which would go on to explore Titan in greater detail. As Voyager 2's time at Saturn came to an end, it had already made history. Its data on the planet's rings, moons, and magnetic field far exceeded previous expectations and sparked new questions about the formation of ring systems and the potential for geological processes on icy moons. But the journey wasn't over yet. The spacecraft had one final destination to reach: Uranus. Voyager 2's arrival at Uranus in January 1986 marked another historic milestone. It remains the only spacecraft to have ever visited the ice giant, making this flyby a unique achievement in space exploration. Uranus is an intriguing world, tilted at an extreme angle, causing it to spin on its side and experience extreme seasonal shifts. This unusual tilt also leads to a magnetic field orientation that differs from that of the other gas giants Voyager 2 had already visited, such as Jupiter and Saturn. The spacecraft's flyby of Uranus provided scientists with a wealth of new information. The planet's mysterious atmosphere, which contains a significant amount of methane, was studied in detail. Voyager 2 also examined the planet's ring system, which, though smaller and more difficult to detect than Saturn's, provided insights into ring formation and dynamics. The flyby allowed scientists to capture close-up images of Uranus's moons, revealing varied surfaces and geological features. Miranda, one of Uranus's moons, intrigued researchers with its strange and fractured surface, suggesting a tumultuous geological history. While the flyby at Uranus was a major success, it also presented new challenges for the mission team. The spacecraft had to cope with a further decrease in power as the plutonium in its RTGs continued to decay. The team worked diligently to manage the spacecraft's energy needs, turning off non-essential systems and ensuring that the most important scientific instruments remained operational. The cold environment of deep space, particularly near Uranus, also required careful management of the spacecraft's heaters to prevent its systems from freezing. Yet despite these challenges, Voyager 2's systems performed admirably, ensuring that it could complete its observations and continue its journey. After completing its flyby of Uranus, Voyager 2 continued to press on toward its next target, Neptune. The spacecraft's power levels were declining, but the team was determined to keep it functional for as long as possible. As it moved farther from the Sun, the spacecraft's ability to generate power continued to decrease, but the incredible legacy of its mission pushed the team to ensure it could continue transmitting data back to Earth for as long as possible. And that brings us to the culmination of Voyager 2's journey thus far. The probe's remarkable achievements across multiple decades have defied expectations, making it a symbol of human curiosity, innovation, and perseverance. Despite the inevitable slowdowns due to its power constraints, the wealth of information Voyager 2 has sent back has expanded our understanding of the outer solar system and beyond. It's a reminder of how far humanity has come in exploring the cosmos, and how much more there is still left to discover. The data from Voyager 2's flyby of Uranus revealed unexpected and intriguing findings. It was determined that Uranus's magnetic field was indeed tilted, but in an unusual way. Instead of being centered around the planet, the magnetic field appeared to be offset, which caused its magnetosphere to wobble unpredictably. This discovery raised questions about the dynamo processes in the planet's interior that might be responsible for generating such a peculiar magnetic field. Additionally, Voyager 2 provided further insight into Uranus's faint ring system. Ground-based astronomers had suspected their existence, but the spacecraft's close-up images gave a more accurate understanding of the ring's arrangement and particle composition. Uranus's moons also revealed unexpected features. Before the flyby, scientists assumed that the moons were inert, icy bodies pocked with craters. However, detailed images of Miranda showed a chaotic surface, with enormous canyons, ridges, and patchwork terrains. The complexity of its landscape suggested that these moons might have experienced geological processes like partial melting or tectonic-like forces. Other moons such as Ariel, Umbriel, Titania, and Oberon, while less dramatic than Miranda, also displayed signs of geological activity in their past. The data from Uranus also upended previous assumptions about its atmospheric activity. While scientists expected the planet to be relatively featureless due to its distance from the Sun, the images revealed subtle cloud banding and faint bright spots, indicating that there were dynamic cloud structures at work. Even though Uranus receives much less warmth from the sun, the planet was not as calm as initially thought. Infrared measurements supported the idea that Uranus may be losing heat more slowly, though the specifics of its internal processes remain a topic of debate. One of the most important aspects of the Uranus flyby was that it provided scientists with valuable information about how an ice giant like Uranus differs from a gas giant like Jupiter or Saturn. Uranus's interior contains significantly more ices, such as water, ammonia, and methane, than its larger counterparts. The gravity and magnetic field data gathered by Voyager 2 suggested that Uranus has a layered interior with a rocky core, an icy mantle, and an outer envelope. This layered structure provided scientists with clues about the formation of the solar system. However, with only a single flyby and limited measurement time, many critical questions remained unanswered. After the successful encounter with Uranus, Voyager 2 used the planet's gravity to help it pivot on its course, setting the stage for its journey to Neptune. This gravity assist was crucial, as it provided the necessary energy for Voyager 2 to reach the outermost major planet in the solar system within a few short years. The success of this maneuver proved the viability of NASA's Grand Tour mission, and the Uranus flyby was regarded as a technical triumph. In August 1989, Voyager 2 reached Neptune, completing its grand tour of the outer solar system. This was the first time Neptune had been observed up close, and Voyager 2's success in operating so far from Earth was a monumental achievement. By the time it reached Neptune, the spacecraft had been in operation for 12 years, far surpassing its original design life. Neptune's striking blue color, supersonic winds, and dynamic atmosphere provided scientists with a wealth of new data. Voyager 2's images revealed swirling cloud formations, massive storms, and a large dark spot, which resembled Jupiter's Great Red Spot. This discovery defied scientists' expectations, as they had assumed Neptune's atmosphere would be relatively inactive due to its distance from the Sun. Instead, Voyager 2 found evidence of dynamic weather driven by Neptune's internal heat. The spacecraft also recorded the fastest winds in the solar system at Neptune. The dark spot's disappearance in later Hubble observations confirmed that Neptune's atmosphere is highly variable. Even at such a great distance from the Sun, Voyager 2 also studied Neptune's magnetic field, which, like Uranus's, was tilted and offset from the planet's center. This observation reinforced the hypothesis that ice giants generate magnetic fields differently from gas giants. Additionally, Voyager 2 discovered Neptune's faint ring system, which consisted of arcs rather than continuous rings. Scientists theorized that these arcs were likely influenced by small moonlets or other gravitational forces. The spotlight was stolen by Triton, Neptune's largest moon. Voyager 2 made an astonishing discovery. Nitrogen geysers were actively venting from Triton's surface, an unexpected finding considering the moon's cold temperatures. The moon's surface featured strange cantaloupe-like terrain and cryovolcanic activity, challenging the assumption that icy moons were geologically inert. Furthermore, Triton's retrograde orbit suggested that it might have been captured from the Kuiper belt. With the successful flyby of Neptune, Voyager 2 had completed its planetary tour and began its interstellar journey. The spacecraft, now heading toward the boundary of the heliosphere, had already achieved a series of remarkable milestones. As Voyager 2 journeyed beyond Neptune, it entered the outer reaches of the solar system, where the sun's wind forms a protective bubble known as the heliosphere. This region, created by charged particles emitted from the sun, shields the solar system from some cosmic rays. Scientists were uncertain where the heliosphere ended, with estimates ranging from 50 to over 100 astronomical units. Voyager 2 carried instruments designed to detect changes in particle density, temperature, and magnetic fields. These instruments provided invaluable data on how the solar wind decreased in speed and pressure with distance from the sun, and how the heliosphere interacted with cosmic rays from outside the solar system. As Voyager 2 traveled further into interstellar space, it continued to gather unprecedented data on the boundaries of the heliosphere. The spacecraft crossed through the termination shock, where the solar wind slows from supersonic to subsonic speeds. The boundary of the heliosphere shifted due to solar activity, and Voyager 2's data helped scientists study how solar cycles influence the shape and dynamics of this protective bubble. The spacecraft also detected fluctuations in plasma populations, cosmic rays, and magnetic fields, illustrating that the heliosphere is a dynamic, ever-changing entity rather than a fixed structure. Despite facing challenges with diminishing power, Voyager 2 systems continued to function and provide valuable data. The spacecraft's power source, its radioisotope thermoelectric generator, RTG, loses energy every year, forcing engineers to prioritize key instruments and sometimes shut off non-essential systems. Still, Voyager 2's ability to operate in such extreme conditions is a testament to its robust engineering. Voyager 2's journey into interstellar space began to provide new insights into how our Sun interacts with the galaxy. In November 2018, NASA announced that Voyager 2 had officially crossed into interstellar space, becoming the second human-made object to leave the Sun's influence. The spacecraft's instruments detected a noticeable increase in cosmic rays and changes in plasma density, confirming that it had left the region dominated by the Sun's outflow. This event, which took place around 120 astronomical units from the Sun, marked a historic moment for humanity's exploration of space. As Voyager 2 entered interstellar space, it faced new challenges. The signals from the spacecraft became faint, requiring NASA's Deep Space Network to employ advanced antennas and sensitive receivers. On average, it now takes more than 18 hours for a signal to travel one way, making communication a slow and complex process. However, each piece of data collected by Voyager 2 remains invaluable to scientists, offering new insights into the nature of interstellar space and our place within the broader universe. Even as Voyager 2 ventured further into the unknown expanse of interstellar space, it continued to send back data that deepened our understanding of the cosmos. One of the most significant challenges faced by the spacecraft was the diminishing power supply. Over the years, the spacecraft's radioisotope thermoelectric generator, RTG, lost energy, forcing engineers to prioritize which instruments would remain active. The team at NASA faced tough decisions, sometimes shutting off heaters and risking the failure of sensitive instruments. Despite these constraints, Voyager 2's robust design and engineering allowed it to continue gathering valuable scientific data, well beyond the original expectations for its mission. As the spacecraft ventured farther, its journey provided new insights into the behavior of cosmic space. One of the most surprising findings came from the data collected by the spacecraft's plasma science instruments. These instruments tracked the changing characteristics of the solar wind, which slowed down as it left the Sun's direct influence. Voyager 2 crossed the boundary of the heliosphere multiple times, with solar activity causing the boundary to shift over time. Scientists were able to study how the solar wind interacts with the interstellar medium, revealing important information about how stars like our Sun influence their cosmic neighborhoods. In addition to its exploration of the heliosphere, Voyager 2's cosmic ray subsystem monitored high-energy particles from beyond our solar system. These particles, mostly originating from supernovas and other energetic astrophysical events, became more prominent as the spacecraft moved further from the Sun. The spacecraft's measurements of cosmic rays provided key insights into how the heliosphere acts as a shield against these high-energy particles and how solar activity influences the cosmic radiation environment. Voyager 2's ability to study these cosmic phenomena was groundbreaking, as no other spacecraft had ventured so far from Earth to directly observe the boundary between our solar system and the interstellar medium. Its data offered scientists a new perspective on space weather and the way stellar winds propagate across vast distances, reshaping our understanding of the Sun's influence on the wider galaxy. These observations were particularly important for refining theories about how other stars and their solar systems interact with the surrounding interstellar medium. In November 2018, the long-awaited announcement came that Voyager 2 had officially crossed into interstellar space, marking a monumental milestone. It became the second human-made object, after its twin Voyager 1, to leave the solar system and enter the vast expanse of interstellar space. This event took place about 120 astronomical units from the Sun, farther than any spacecraft had ever traveled before. Voyager 2's instruments detected a sudden increase in cosmic rays and a shift in plasma density, confirming that it had moved beyond the Sun's direct influence. The spacecraft's magnetometer also recorded changes in the magnetic field, suggesting that the interstellar magnetic field was interacting with the solar wind in complex ways. The transition into interstellar space did not occur in the dramatic fashion that some had anticipated. Instead of an abrupt change, scientists observed that the boundary between the heliosphere and interstellar space was more nuanced. The magnetic field did not immediately realign in the way some models had predicted. This complicated interaction between the Sun's magnetic field and the local interstellar environment added new layers of complexity to our understanding of how stars and their magnetic fields influence the broader galactic medium. Scientists are still working to interpret the data from this interaction, which could have broader implications for the study of other star systems. As Voyager 2's journey continues, the spacecraft's role as a pioneering explorer remains invaluable. Its scientific observations have opened new frontiers in our understanding of the outer solar system, the heliosphere, and now, the vast reaches of interstellar space. With each piece of data, Voyager 2 is providing humanity with insights into the conditions of the cosmos that were once thought to be beyond our reach. Despite the challenges of communicating with the spacecraft, which now requires more than 18 hours for a signal to travel one way, Voyager 2's mission is far from over. Each transmission, though slow and faint, provides precious data that continues to shape our knowledge of the universe. The spacecraft's legacy is one of resilience, exploration, and a commitment to expanding the boundaries of human knowledge. In many ways, Voyager 2's crossing into interstellar space represents the culmination of humanity's desire to explore the unknown, to push the limits of technology and scientific curiosity. As it ventures farther into the depths of space, it becomes a symbol of human achievement and a reminder that the quest for knowledge knows no boundaries. Voyager 2 is no longer just a spacecraft. It is a trailblazer, carving a path through a region of space that no other human-made object has traveled. Its continued journey into interstellar space is a testament to the vision and ambition of the scientists, engineers, and mission planners who made it all possible.